In this video, we're going to be looking at orbits / shells, subshells, and orbitals. So first, let's look at orbits. First, we thought an atom would be like the smallest particle known to man, but it just so happens that although it's unimaginably believed size, it can be split even more through protons, neutrons, which are neutral, and electrons, which is negative. Basically, the way it's classified is you have protons, which are positively charged, and then you would have the electrons, which are negatively charged, located all around over here. And you would have also the neutrons, the neutrally charged, and basically the positively charged would attract to like the negatively charged ones. That's how the electrons will move around the nucleus, and that's how we typically picture it. So we're going to be looking at a Bohr model, and if you're unsure what a Bohr model is, if you were to look over here, this is how a Bohr model would look like. So basically, back then, scientists were having questions upon how everything was configured and how they were supposed to classify / organize it. And the Bohr model kind of made sense, and it gave them a much more simpler thought towards how the atom would be structured, even though an atom would be structured way more differently than what the Bohr model suggests. Since the Bohr model, even though it looks much more like different than what the actual atom looks like, we still use it because it is much more simpler to explain. So basically, we're going to be looking at 4 shells, okay? So we're gonna have the nucleus here, then the first shell, second shell, third shell, fourth shell, okay? And this first shell, we're going to name the first shell n equals 1, second shell n equals 2, third n equals 3, and then n equals 4. It is also given letters, so like K for the first one, L, M, N, okay? However, let's first start off with the numbers. The reason why the chemists and other scientists used numbers for it was to figure out how many electrons a shell could carry at its maximum peak. So, Bohr created a formula, and this formula was 2 times n squared equals the number of electrons there are. So as per Bohr, each orbit can contain the amount of electrons there are if we were to substitute it based on the number. So let's look at the second one. Let's just take the second one. It's the second ring, for example, okay? So 2 times 2 to the 2 squared, what do we get? 2 squared is 4, and 4 times 2, that's 8. Meaning the second one can only hold 8. And if you were to look over here at this chart, that's correct. And now, if we were to apply it to something like 3, 1, 4, we would get these numbers, and these numbers tell how many electrons each orbit could hold maximum. So we also used letters to classify it. So K would represent the first one, L would represent the second one, M would represent the third one, and N would represent the fourth one. So now you might be wondering, why do we have 4 different shells? Why can't it be organized more simpler? Well, the electrons, there's different powers, like there's a different attraction each electron can have towards a nucleus. So if an electron has more energy, if it has the most amount of energy, it can be put to the n. It could be put to this n or the fourth ring over here because it has such a big attraction that staying over here would make more sense because it needs a big distance for the energy to equalize with the rest. If it has like the lowest energy, then it would be over here in this first circle. The electron would stay in this first circle, K, because it doesn't have that much energy, and because it is negatively charged, and because it is closer towards the positively charged protons, it would need that very small distance to be able to stay attracted. Because if it was all the way here, that electron would just be floating off. Orbits is basically a path where electrons revolve around the nucleus based on the energy and the number of spots there are. So now let's move to subshells. So we just talked about how there's this K, L, M, N, or shell 1, 2, 3, 4. Well, this can be classified this could be divided into more stuff. This is called subshells. So there are 4 different types of subshells: subshell S, subshell P, subshell D, and subshell F. So the way it's classified is like this, okay? So since the first shell, it doesn't have that many spots, there's like only there's only 2 electrons, it makes more logical sense that there will be only 1 subshell. However, the second one, since it's the second least amount of electrons located there, it would make sense there's 2. And for third, it makes sense that there's third, like, it would make sense that there's not as much as the fourth one, so they have 3, and the fourth one, it would have the most, which is 4 different subshells. Here's how they would be located, okay? So if it was 1s, that means that it's located on ring 1 and it's subshell S. But if it's 2s, it's located on ring 2, but it's still subshell S. But if you were to say something like 3d, it's located on the shell 3, but it's located on subshell D. Okay, so that's how you could classify it. Subshells are definitely used to be able to classify the orbitals. But you see over here, per subshell, there's like this certain amount of orbitals. So subshell S has 1 orbital, and each orbital can hold 2 amount of electrons. And that makes sense. The reason why, that is because the first shell, if you look over here, can only hold 2 different electrons. So it would definitely make sense that the orbital can only hold 2 electrons. So if we were to look at the L shell or the second shell, we would see 2 subshells over here, S and P, but there are 4 different orbitals. Now, since each one can hold 2 electrons, as we see over here, there are 2, 4, 6, 8, there are 8 electrons total as per this entire shell. And if you look over here, there's 8. This could be said for the M shell and N shell over here. Let's take an example, okay? Oxygen. This is the atomic symbol. This is their atomic number, okay? That means that there's 8 protons and 8 electrons. So if you understand that there are 8 electrons, that is enough to be able to understand how to be able to categorize this. Let me just draw its orbit, okay? So this is going to be its nucleus. Then it would have 1, 2, and 2 would practically be it, because the first one could only hold max 2, and since there's 8, this can obviously fit. So 1, 2, and 2 minus 8, like 8 minus 2 is 6, meaning this one can hold 6. And since it can only hold max 8, that definitely means that 6 can hold in the second shell. So 1, 2, 3, 4, 5, 6. So now that we see it in an orbit, let's see how we can actually classify it based on looking at it numerically. So we see S over here, but there's 2 of them, so we would put to the power of 2. Then we would put 2s because it's located on the second shell. And if you want to make it clear, this could be 1s, because 1s means it's located on the first shell, and an s2, like s squared, means that there's 2 electrons. Then there would be 2s, and since s can only hold 2 different electrons, that would be its max. But then of course there's 2p. 2p meaning it's located on the second shell, on the p subshell. And see, look, 2 plus 2, that's 4. So that means that 8 minus 4 means there's 4 remaining. So we have to put 4 here. So 2 plus 4 gives you 8. Hence, we get the atomic number 8, meaning that this is how you actually write it. This is how you would write it based on its electron configuration, on its subshells and shells and orbitals. I'll give you another one. It's sodium, okay? So let's flip to the back here. Sodium looks like this, and its atomic number is 11. So let me just draw it real quick. So this is its nucleus, first shell, second shell, third shell, okay? So the first one, as you can see, can only hold 2. So 1, 2. Second shell can hold max 8. And since it's 11, we can put 8 in the second one. So 1, 2, 3, 4, 5, 6, 7, 8. And now 2 plus 8, that's 10, but we only have 1 more. So this would be our valence electron 1, okay? So let's look at it again. One, so we would have on the first shell, we would have 1. And since the first shell only has subshell S, that means we would put S. And since there's 2 electrons, we would put 2. Now we would have 2s, and of course square, and then 2p. So this second shell over here, it has 8 electrons. And since over here we said that the s subshell already took 2 away, that means 6 is remaining. So we would have 2p6. But now let's look at it. We have a third shell, and since the first subshell that we find is s, we would put 3s to the power of 1. And this is our electron configuration. Basically, the difference between orbitals / shells, subshells, and orbitals is that orbitals are classified into 4 different rings. Those rings are K, L, M, and N. And we can use the formula 2n to the n squared to get the amount of electrons there are based on Bohr's model. The shell can be split into a subshell or subshells based on the amount of electrons they currently are, and also based on the power or energy each electron has. So we would see over here for the last one, it would have the most amount of subshells, but for the first one, it would have the least amount of subshells because there's the least amount of electrons and the least amount of energy located there. Also, based on each level over here, we would see that energy between the electrons would change based on the attractiveness it has with the protons. And then lastly, we would have the orbitals. Subshell S has only 1 orbital, meaning it can hold 2 electrons. P has 3, so 6. D has 5, so 10. And then F has 7, so 14. This is all about orbits, subshells, and orbitals.